Hello, once again, geology enthusiasts. We are back for another exciting episode of Geologic Time. And today we're going to fully get into the Mesozoic Era, 245 million years ago to about 66.4 million years ago. But before we do that, let's review where we've come from because it's been quite exciting. So we ended the Paleozoic era with the Permian extinction. The Permian extinction is also known as Fireball Earth or the Great Dying. And what we saw was the Permian extinction was the largest mass extinction on record, where 95% of all marine life die and 80% of all vertebrate life on the planet dies. So certainly the most significant extinction that we've seen up to date. The second largest extinction that we saw was the Ordovician. And so we're making some comparisons between the Ordovician snowball Earth versus the Permian fireball Earth and the drastic changes between those two different scenarios. So where we're at now is we're coming out of a mass extinction and we're moving into the Mesozoic Era. So the Mesozoic Era is going to be known as the time of the dinosaurs. So the Mesozoic Era, just to review, contains the Cretaceous, the Triassic, and the Jurassic. And to review where we're at based on our landscape, we have completely built the North American Cordilleran on our western seaboard. The Appalachians have been completely created. And as we're moving through the Cretaceous to the Triassic, we are just in those final phases of building the last supercontinent in Pangea, and they'll hang out for a little bit and then they'll begin to move away. So the majority of our land masses then are equatorial. And this is a good representation of that. So you're seeing the top diagram, and that's going to represent Cretaceous to the Triassic. And then in the middle of the Triassic, we're going to start to break apart that Pangea cycle. And so towards the latter part of the Mesozoic, you're going to start to see the proto-Atlantic Ocean. So you're going to see that divergent plate boundary begin to spread. Another interesting thing to keep in mind is that we, well, in addition to like when you have those Pangea super continent with the continents all up against each other, you're changing your weather patterns. But this is also going to provide some pretty substantial land bridges for migration of these large dinosaurs that we're going to see uprise in the Mesozoic. So land masses where dinosaurs can move from one place to the other quite easily. And that's going to be, that was one of the tools that Alfred Wegener used, was looking at specific index fossils and tracing them from continent to continent. Because he said, like, how could the Lysosaur get from North America to Europe unless those continents were combined? Because there's obviously an ocean in between us now. And remember, Lysosaur was not meant to swim. It was freshwater dwelling. So the position of those land masses are going to be important. It's going to change the type of climate that we see. So most of the continents are towards the equator. So you're thinking of more tropical climates. And the Appalachians are completely formed. And remember, they're significant in height. So they're, at least as tall as the Himalayan mountain range. And so when we start to see the breakup of Pangea in the Jurassic, what's going to happen is that those East Coast land masses are no longer convergent. And so you're going to end up with erosion that happens. Differently, our West Coast, the North American Cordillera, continues to be formed because it is a convergent plate boundary. So we're thinking about this subtropical environment as we move forward into the Triassic. So, and we start with the Triassic because it takes a good portion of the Cretaceous just to kind of get the climate stabilized again after coming out of the Great Dying and the Permian extinction. So the real magic is going to, and the real rebound of life is going to begin in the Triassic era. And just like we've seen time and time again, coming out of these major and significant extinctions, the stromatolites are going to be our heroes. So the stromatolites are going to rebound, remembering that they're photosynthetic, so they're taking that carbon dioxide out of the atmosphere, respiring oxygen, and helping to find that stabilization of Earth's surface temperature so that other life can rebound. And so other basic things that we've seen that have been so important that we saw uprise in the Cambrian and the Ordovician. So we start to see the brachiopods and the bryozoans and phylum Mollusca begin to rebound. So what's interesting is that as we've seen coming out of each of these mass extinctions, we're having to redevelop the food web. And it is the development of that food web that again establishes the stabilization on the planet for at least a little bit of time. Beyond the gastropods and the bivalves, all other invertebrates are going to remain pretty rare until again there's stabilization in the atmosphere and in the water column. But once that happens and you start to see the rebound of the other invertebrate life, we're going to see an explosion, which is often referred to as the Mesozoic marine revolution. So you're going to see again another escalation of predators with these anti-defense mechanisms, and specifically the development of things with very large and serrated teeth are going to be found in the fossil record. So you're looking at a picture of a scientist, and he is standing within the jaw of a megalodon, and he is holding the jaw of a great white shark. So we see the great advancement of filling in the ecological niches of the ocean. And we started to see that, didn't we, in the Permian with things like the continued uprise of different phylum chordatas. But here we really see the advancement of filling in the water column, similar to the Ordovician. The picture at the bottom with a tooth, that's a example of a megalodon tooth. And to give you some size comparison, here is this chart, and I just think this is fascinating. So on the lower left-hand side of the chart, you're comparing the largest ever recorded great white shark. And so, yeah, at best, the scale's on meters on the x-axis. So about 6 meters. 6 meters is less than 20 feet. And then you compare that to the average of the estimated megalodon, which is up to 20 meters in length. So we're talking a significantly bigger version of a shark in the oceans. And they also compare it to a diver up there on the little screen. So paleontologists and geologists just really love talking about the megalodon. I'm going to post a little video for you to watch about some size comparisons of the megalodon. But it is it's fascinating. It's going to go extinct when the dinosaurs go extinct. So we won't see it for much longer. But we see its very first signatures within the Triassic. So there's a lot of fun videos that compare the megalodon to the Dunkleostasis, and if they're in a fight, who would win? Remembering that Dunkleostasis had a big barbed armor that protected its neck and bony plates. So it's kind of fun to think about. So if you introduce a megalodon to the Triassic, megalodon has to have something to eat. And so remembering within phylum Chordata, we started to develop acanthidians before the Permian extinction. And so we start to see the rise of much larger finned fish. And so they have greater mobility, and they're going to be a great food source for megalodon that is ginormous in size and who's going to have a whole lot of food sources to be able to eat. And then we also get to see the uprising of placoderms. And placoderms are related to, are essentially very early turtles. I think they're quite cute. What we're going to do as we move forward is we're going to look at the structure and capacity of their brain and also their teeth. So as we move forward talking in terms of reptiles and things that develop in the Triassic, the skulls become very important. And so for the Placodon, what you notice is that they have really blunt teeth, but they also have teeth in the front that allow them to be like grazers. So we're making some comparisons between those that are predators and those that are scavengers, and kind of looking at the role of them as we recreate the food web of the Triassic. So Placodons have a harder body casing armor, and they do have mobility. And so what we're thinking about is recreating what these Mesozoic oceans might look like initially. So you've, of course, got your brachiopods, your bryozoas, your stromatolites are coming online, your gastropods. Then you're building up the phylum Chordata with your ostracoderms and your acanthidians, and other things that we see is like Placodons. And then a thing that's called a plesiosaur is going to become quite popular, and we find them as an index fossil for the Triassic. And so a plesiosaur is the one that looks like what you might know as brontosaurus. Brontosaurus is not the right word. It's actually called an apatatosaurus. But it has fins instead of feet. So these are completely aquatic reptiles that are living within the water column. And so they're quite prevalent within the Triassic. So this helps us to kind of recreate what those Triassic seaways started to look like, and all of the intimidation of these large creatures within the oceans. So we have our ocean life that's rebounding, and now we also see a rebound of life on land, because don't forget that when you're coming out of a major mass extinction, your kingdom Animalia has taken a big hit, but also other things on the planet that include kingdoms Monera, Protista, fungi, and plantae. So they're all having to rebound themselves. And they do, but what's interesting is that we start to see new things arise on the planet in kingdom plantae. And specifically, we start to see how spore-bearing plants are going to rebound and how ferns are going to dominate. And within those, we're going to see gymnosperms for the first time, and that includes the cycad, as pictured here in the left-hand corner. A common cycad moving on. Additionally, we also see hardwood trees that begin to evolve. And this is the first time that we've seen a true hardwood tree. So we look to finding conifers in the fossil record, and also ginkgos. And so ginkgos have that unique kind of like heart-shaped feature. And oftentimes when we find ginkgos in the fossil record, they are preserved by carbonization, because they have a lot of that chelatin in their leaf system. So they provide a good record of staining. And we still have ginkgos, obviously, and hardwoods on the planet today. So the very first time that these Triassic forests began to rebound and initiate is in the Triassic. And I like to show this picture because it kind of gives us a different representation of what we might think the Triassic to look like. So remember that we're kind of like a subtropical environment with more tropical plants closer to the equator. But remember that we do have some latitudinal diversity as we move away from the equator. So you would expect to find some of those harder wood trees farther away from the equatorial region. So our environment has rebound from that nasty mass extinction. And one of the things that's going to be exciting about the Triassic is going to be the uprising of yet another transitional species. And this transitional species is going to be called Archaeopteryx. And so Archaeopteryx is going to be in between a reptile that we saw uprising in the Permian and a bird. So like when we try to answer the question, which came first, the chicken or the egg? The egg came first, didn't it? Because we see that first in the Permian record. So now you have an argument for that discussion. Yeah, we see the uprising of the amniotic egg first in the Permian with the uprising of the reptiles. And what we know from Archaeopteryx and finding this fantastic specimen is that reptiles evolved into birds. So chicken or the egg? The egg came first. Here is a picture of Archaeopteryx. Archaeopteryx is kind of like the size of a turkey. So not all that big, but it's about the size of a turkey. It kind of has the posture of a turkey, but like when you look at its head, it still very much has the head of a lizard. So you're imagining a bird with this reptilian type face and scales and teeth. And then when we look at the imagery, you notice that it still has a long reptilian tail. The difference is that tail and its arms are now covered in feathers. These are not flight feathers. So there's a difference between a flight feather and a non-flight feather. So you're kind of comparing like a peacock or an ostrich versus a flight bird. And so the difference is that like a peacock feather is one that is symmetrical. So you get, it has symmetry, whereas a flight feather is one that is asymmetrical. And so we see non-flight feathers on this initial Archaeopteryx specimen. That is a transitional species, but they are in fact true feathers. Again, it's got the reptilian feet, like feet. And then just like our homology demonstration and the principles of vested structures, the idea is that everything in Kingdom Animalia has similar structure. And so even looking at this diagram of Archaeopteryx, you know that it has claws, it has those finger capacities. And so in recreation of the behavior of the initial Archaeopteryx, this transitional species, it's thought that it probably didn't fly, like it probably could hover enough to get off the ground, kind of like a turkey. So probably like nested in short trees or like in foliage that was off the ground just to get away from predators. But instead, it was able to use those claws maybe to climb a little bit higher in the tree. So using the claws on its feet, but also the claws that still remained on its wings. So what's interesting about Archaeopteryx is it wasn't found until the 1980s. So it was always suspected that there would have been a link from a reptile to a bird based on that presence of the amniotic egg. But this specimen created a smoking gun. And hopefully you'll zoom into that replica that's on the bottom. I also have one in my laboratory, but it is a beautiful species. And when you zoom in, you can see the impressions of the feathers, and you can see the well-defined claws, and you can see the well-defined tail. So it was great to be able to find this because it provided that link of lineage that we needed in the fossil record. So like we've talked about, you know, where it's exciting, geology is exciting because you're always filling in the gaps, the missing pieces and the missing gaps. And so Archaeopteryx helped us to do that. This diagram on the screen gives you a little bit a different visual representation. So Archaeopteryx is in the center. On the top, you have a theropod, which is essentially a small reptile. And then you have the skeleton of a bird on the lower part. So you see the chicken. What's interesting is when we start to talk about dinosaurs, like true dinosaurs, we're going to talk about the difference between a reptilian hip position and the position of a bird hip. So the tilt of the pelvis is a little bit different. And within the Archaeopteryx, you can see how the pelvic tilt is progressing a little bit more towards a bird style hip. So the difference has to do with like the walking mechanisms. So something that is bipedal is going to be a little bit more upright than something that is more bird-like. So the position of the hip is going to be a little bit different. So now what's in the Triassic, we've built all of our environments. So we have our aquatic environment, we have our land environment with reptiles and amphibians, and now we're building up space in the vertical, in the tree line, which we hadn't seen prior to this. So we've got all these different spaces that begin to be filled. And so we mentioned when we talked about the complexity of life, we said that is different order than the uprising of life in the fossil record. So we saw Kingdom Monero, Kingdom Protista, Kingdom Animalia, then we saw Kingdom Fungi and Kingdom Plantae. When we think in terms of Kingdom Animalia in the Triassic, we have seen amphibians and reptiles and birds, and of course our fishes and invertebrates that are living in the ocean. But we also have to consider the fossil record of small mammals. And so remember, like, this is the first signature. We find evidence of small mammals in the Triassic record, but they're not going to be much more bigger than a cat. And a lots of times they're going to be like little ground mice and like smaller versions of rabbits and maybe even like squirrels that are moving towards the trees that have mobility. The difference between a mammal and other things is that a mammal gives live birth, it has true hair, and it is endothermic, so it's able to regulate its own heat. So we do start to see evidence of those in the Triassic and the Mesozoic. They're probably snacks for the velociraptors that were running around like this picture wants to show you, but they're not going to become dominant, and that's because remember that the reptiles have a big jump on progression. So we started to see the very first reptiles in the Permian. So they've got 100 million years of advancement over these small reptiles. So the reptiles are just going to be able to explode. And remember, like, the conditions allow for those reptiles to explode because Pangea is equatorial. So reptiles thrive in environments that are warmer. And remember, we're coming out of the Permian that was called Fireball Earth, right? And so we're still dealing with climate that is relatively hot and humid, and in some capacities even drier in the middle interiors of that supercontinent that has formed. So the mammals will have their day, but that day is going to come in the Cenozoic. So let's chat now about the uprising of dinosaurs. I know you guys will love this. So again, when we talk about dinosaurs, we separate them into two groups. And those groups are going to be the Saurischian group and the Orontian group. So the Orontian group is going to lend themselves more towards a bird-style pelvis, and then the Saurischian group is going to lend itself more towards a reptilian hip. So if we look at this diagram on the bottom, the reptile hip will be the lineage that moves to the right, and then the bird style hip will lend itself to the lineage on the left. And so we can categorize some of our biggest and baddest dinosaurs within these two different groups. And that's really what I want to do for the purposes of a introductory class that talks about dinosaurs. So let's move forward and talk a little bit more about this. Here's a nice diagram that separates those two groups. So the top is the Saurischian, the bottom is the Orontian, and you can see just the position of the hip is a little bit different. And so the mobility of these dinosaurs is going to be a little bit different. When we think of the Saurischian group, we are going to think in terms of our bigger dinosaurs. So looking back at the diagram that's on here on the left, we're thinking in terms of like the T-Rex. With the bird style hip, we're thinking of things that are moving maybe a little bit slower, like the Stegosaurus. So mobility is going to come into play. As we see on the screen here, we can have in both groups those that are bipedal and those that are tetrapods. So if they're bipedal, they're walking on two legs essentially. If they're tetrapod, they're walking on all four. So we're going to start with the Orontian group, and these are just a few of my very favorite dinosaurs, and I think you'll like them too. So when we talk about a bird-like hip, by definition, we're looking at the pubis bone that's rotated backwards. So this picture on the lower right-hand corner helps to illustrate that. So the pubis bone is rotated backwards. Additionally, another characteristic of this group is when we look at that skull cavity, we're looking at the connection of the predentary bone, which is the upper jaw, and the lower jaw. And so the predentary bone of the upper jaw is going to cap the front of the lower jaw. So it's almost like he's got an overbite. And typically when we look at the Aurantian group, they're going to have a toothless snout. So remember, we talked about the placoderms. When we saw the placoderms in the Paleozoic, the placoderms had teeth on its snout, was able to scourge around the bottom of the seafloor a little bit. Here we're thinking of a snout that is usually toothless. And in addition to have a toothless snout, another characteristic is usually it has really well-developed cheeks. And so those cheek cavities, as you can see in this picture here, is to have the ability to hold vegetation while chewing. So what you can imagine is that typically the Aurantian style group are preyed upon. Yeah, and maybe you can even get an idea of what you think this dinosaur is by looking at its, excuse me, the shape of its skeleton, and by looking at those cheeks, and I bet you've guessed it right, because this is the dinosaur that we all know and love called Stegosaurus. So Stegosaurus is an Aurantian type of dinosaur, and also characteristic of these guys is that they're typically herbaceous, and you know that from the shape of their teeth. Like, they're not typically sharp or serrated. They're usually more blunt. They have a toothless snout, and they're usually herbaceous. And so these guys are filling in the food chain for some of the bigger and better dinosaurs. And they have at least five vertebrae. So here we have Stegosaurus, one of our favorite dinosaurs. Stegosaurus has those scapulas. So remember when we introduced plesiosaurs, we talked about them being mesothermic, meaning that they could regulate their temperature by raising or lowering the fan. There's some current discussion as to whether Stegosaurus is also mesothermic, because perhaps maybe they were able to use the scapulas on their back to be able to regulate their temperature. And so there's some discussion as to, if you look at these scapulas up close, like the picture on the lower right, as to if those are actually like blood vessels that run through them. So again, like being able to act as a radiator to radiate heat or absorb heat. So that's what's fascinating about paleontology, is that we're still able to ask these questions and have these discussions. This Stegosaurus. Also in the group of the Orienthintias is the Ankylosaurus. If you've ever been to the Telos Museum in Northwest Georgia, they've got a fantastic replica of an Ankylosaurus. And the cool thing is, and the big thing that determines Ankylosaurus is its tail. So it always has an armored plate on its back, and it always has an armor on its tail, and that was its greatest defense mechanism. So very similar in shape when you look at the skeletal features of a Stegosaurus, with a low slung head and the position of its tail. The other advantage of Ankylosaurus, though, was it's thought that when there was prey and predation, it would hunker down into a ball, and then the bony part of its back would protect it. It's got a bony head plate that would protect it, so it's got some type of armor, and then it would just swing its tail. How effective that was, I guess we can only imagine, but it might have been strong enough to move away velociraptors that were trying to prey upon it, because it did have pretty significant armor type of plates. And then we can talk about Triceratops. And so Triceratops is known for that big, also armor plate. it is also a tetrapod, so it's able to run on fours, and it's thought to be pretty quick. But the challenge is when you're running and when you're Triceratops, you've got all this weight around your head. And so lots of times in the paleontological record, when they're finding the fossils of Triceratops, it usually has a broken lower jaw, because you're imagining Triceratops running and it trips and it falls with all that weight. So it's kind of got this forward momentum, and so you see a lot of Triceratops with fractures in its lower jaw. T-Rex too has a similar type of problem. With T-Rex with Triceratops, what you can notice just from these different pictures here is that Triceratops can have two horns or one horn, kind of similar to like a modern day rhino. And there's a lot of variation in the species depending on the shape of the skull, but the overall idea of Triceratops is the same. So then the second group that I want to introduce is the Syrinchian group. And so this is called the reptilian hip. And so in this case, the pubis bone is pointed forward. And because of that, it's going to allow it to be able to hold a lot more weight. So there's a lot more stability when you have a reptilian hip compared to a bird-style hip. Another indicator that we see in the Syrinchian group is that its vertebrae are elongated and they are rearward facing. So this image might be familiar to you. You've seen the movies Land Before Time, so they call it a brontosaurus. That's not the right name. It is an apatosaurus. But these dinosaurs that have these really long necks have to have rear-facing vertebrae because their spinal cord is essentially in the front of their body. So you have to be able to hold and have some mobility in those neck muscles, and that's what we see in the Syrinchian group. Different than the Syrinchian group, when we look at the head cavity, the upper and lower jaw are going to meet. So we're talking in terms of being a better predator than those in the Syrinchian group. And you've guessed it, if you're a predator, you can also have claws. And so these claw and large thumb characteristics are common in the Syrinchian group. So most of them are set up to be carnivores. Some of them are herbivores, but they are set up to be some of the biggest and baddest predators ever known on the planet. And they can move either in herds or they can scavenge and hunt individually. And this leads us to our T-Rex, because he is the biggest and baddest dinosaur on the planet overall. And when we look at T-Rex, one of those characteristics is that he's got those little arms, got the big skull cavity, and he's got serrated teeth. And those serrated teeth get really well preserved in the fossil record, so we can find those in abundance. But look at that, the head cavity. So T-Rex is built to be a predator, although there's some controversy as if he might have been a scavenger. And the ideas about him being one of or either of those categories I'm going to talk about in a previous lecture. But he has significant capacity to be a predator, including those large thumbs and including the serrated teeth. Here's a picture of one of the very first T-Rex that was found. This is T-Rex Sue. Sue is on display at the University of Pennsylvania. So we can have T-Rex, and then we can have Apatosaurus, which is seen in this picture. So these massive weight-bearing dinosaurs that have these long necks and that's balanced by these long tails. And lots of times we think that Apatosaurus is just a tetrapod moving on all fours, but there's a lot of tracking evidence, so tracking of those footprints and of its tail, that represent him maybe standing up on his hind legs. So think of the great advantage if you're using that tail to balance yourself and you have this long neck to be able to reach vegetation, because it's thought that Appalachians was a herbivore, and you can imagine how much you would have to eat to sustain that body mass. So the advantage would be to be able to utilize all of the space around you, including your height. Another fun fact about Appalachians is it's thought that he probably had high blood pressure. And that's because you can imagine how much effort it would take for your heart to be able to pump blood all the way up the neck to that very small head. So I keep referring to this as Appalachians, and the story is kind of funny. A scientist had found and put together this entire skeleton of the dinosaur, and this was like in 1910, and he didn't have a skull to go with it, and so he kind of just finds a skull and puts it on it. He names it Brontosaurus, and then many years later, they figure out that the head was too small, and you can tell that by looking at the old pictures of the skeleton. And so when they realized that Brontosaurus had the wrong skull, they renamed it. So I think this was a pretty good introduction onto the Triassic. And unlike other lectures, we're not going to end this one in death and destruction. We are going to end with the happiness that we have developed the reptilian group into Orontians and Strontians, and we started to manifest these fantastic reptiles that have both bird-shaped hips and reptile-shaped hips. So we have both tetrapods and bipedal organisms that are living about and moving about the planet. So I think I'm going to stop here. You've been a wonderful audience, and I will talk to you more about the Mesozoic.